Hi everybody, today I'm going to talk to you guys about Hooke's Law. Hooke's Law is the first of our subjects for waves, and it might not seem like it's related at first, but it is, because we're going to start off our discussion with oscillations. And oscillations are really repeated motions that occur when you have a restoring force. And so probably the most obvious restoring force that you've dealt with in the past has been when you deal with springs. And so Robert Hooke came along and wanted to study this process where you have a spring that can be stretched or compressed, and then he realized that there was a force that was being applied by the spring to be able to change its shape back to what its original position was. And he found that there was a linear relationship, an actual linear relationship between the force that's being applied by the spring to restore it and the amount that you change its position. And so here's Hooke's Law in all of its glory right here. It's formula 9.2 on our formula sheet. It says that a spring force, or any kind of restoring force, is equal to the opposite of K, which is a spring constant, multiplied by the displacement. The opposite sign right here may seem a little strange, but in reality it makes a lot of sense because this is a restoring force, right? This is a force that restores the shape of the object. So for example, if you have a spring that's normally like this in this diagram here, and then you add a weight to it which causes the displacement to be downward, doesn't it make sense that the force would be applied in the upward direction to try to restore that original position and the original shape? And so we say the spring force here is actually back up towards the rest position. Now, Robert Hooke found that the amount of that force is actually directly related to the amounts that you displace the spring. And so it doesn't matter whether it's compressed or stretched. If it's compressed, like so that the original position was maybe like that long, and you compressed its end so that it went in like so, he found that the force would go this way. If you then took the same spring and gave it double the amount of displacement, so that's 2x there, he found that the force that should be applied backwards should be 2f. That's all there is to it. Again, the negative sign there just means they're in opposite directions. The k is kind of special, we'll talk about it in a second, and there's a linear relationship between the spring force and the displacement. The spring constant, which is that k right there, is weird because what it really does is it measures how badly the spring wants to get back to its original shape. And so we would call this the stiffness of the spring if you want to. So the stiffer the spring, the more it wants to get back to its original shape, and therefore the more force is applied to cause it to want to get back, right? To try to change that shape back to what it was originally. There are many, many instances in which objects, for example, like atoms in a matrix, for example, will try to get back to their original position when they are displaced. And those kinds of things do follow a similar type of rule to Hooke's Law. There also, it's kind of interesting that there's a parallel here between this and Newton's second law. Remember, Newton's second law is F equals ma, right? And m is a resistance to a change in motion. K here is a resistance to a change in compression or stretching. So there is a little bit of a parallel there. Just keep that in mind. But that's really it for Hooke's Law. We're going to do some experimentation with it, some simulations, and then we're going to see how if you do apply a force to it or put a weight on it, then you can get the spring to oscillate back and forth because of this spring force. And then that spring force gives it potential energy, which gets converted into kinetic energy and so on. So hopefully that makes sense. I know it was a quick video. Thanks for watching.